how do we use enthalpy change to determine a particular reaction, whether it's exothermic, endothermic, and the official unit for measuring energy is joules. And we also have other units there, calories. Okay, so the first learning objective, we pretty much lay the ground of how we measure energy. And the second learning objective, we introduce this equation Q, the amount of heat being transferred, the energy transferred in the form of heat, equals to C times M, or CS times M, times the change in temperature. So this is what we call the specific heat capacity. M is the mass. Change of temperature, well, when you do change of temperature, by convention, you always use final temperature minus the initial temperature. So if you have something that's hot, a higher temperature, and that cools down later on after the process, well, final temperature minus the initial temperature is always going to be a negative number. Okay? And then if you have, say, when you're mixing ice and hot water together, eventually the original quantity of ice that you have there, well, the temperature of that quantity of water will rise up to thermal equilibrium. So the final temperature is higher than the initial temperature. When you take the difference, and that delta T is going to be a positive number. But when you have hot water, after reaching the equilibrium, the final temperature of the water is going to be cooler or colder than the initial temperature. So when you take the difference there, it's always final temperature minus initial temperature for each of the substances there. And then that number, for the one that releases heat and temperature is going down, this number is going to be negative. Okay? And this is a quantity that's specific to each of the materials. When you have different compound with different chemicals there, this number has each compound has a different value. Now M is simply the mass. Okay, so this equation basically governs the heat transfer. When you have two objects with different temperature, when you mix them together, eventually they will reach thermal equilibrium, meaning they will reach the same temperature. And so if you know the initial temperature for each of the two objects before you mix them, well, the final temperature is the thermal equilibrium temperature at thermal equilibrium. So that final temperature, subtract the initial, will give you the change. Well, the thing here is that when the two objects are mixed together, it doesn't matter how much in terms of mass that you have in there. The total amount of heat transferred from the hot object equals to the amount of heat absorbed by the colder object before the mixing. So that's the key equation to remember there. So this Q could be the heat transferred out of the hot object. It's also the heat absorbed by the colder object. So those two Q's, the heat being transferred should be the same. Okay? So if 1, 2, 3, 4, out of these four quantities, if 3 of them are given directly or indirectly, you can figure them out, and then the fourth one would be your unknown. You will be able to do the calculation. One of the examples that we did is this particular equation, this particular question. So you have 45 grams of hot metal, 100 degrees Celsius. You drop it in water. Water is cold to begin with, 25 degrees Celsius. Okay, so when the final temperature is reached, and final temperature is 37 degrees. So 63 degree is the temperature change for the hot metal, and then 12 degrees is the temperature change for the water. The amount of water, the amount of heat being absorbed by the metal, or being released by the metal, should equal to the amount of heat being absorbed by water. Setting it up, we ask you, in this case, we ask you to calculate this quantity. This is given, well, you can figure that out. These 3 quantities are given. So the only unknown is that CS for the metal, specific heat capacity for the metal there. So you should be able to do the calculation. One thing that I should note here is that this negative sign should be on this side to be consistent with our discussion. Exothermic heat is being lost. Okay, so metal is giving out heat, water is acquiring heat. And also, based on what we just mentioned there, delta T, the change in temperature, final minus initial. So final is 37 minus initial, that's negative 63. Negative 63, you put a negative sign in there, now makes it positive. And then this, on the other side, the water, on the water side there, mass is given. Change of temperature, 37 minus 25, that's positive 12. Okay, so in the textbook there, this is the equation that copied from the textbook there, and in the textbook there, really it doesn't matter where you put the, well, it matters, but in a sense, it doesn't really matter where you put that negative sign, as long as you end up with a positive number for the specific heat capacity there. Okay, so when we were talking about exothermic reaction, we say heat is being released, by convention, heat is being lost. If you stay inside the metal, the metal is giving up heat, so that should be a negative number there. So I apologize for that confusion there, but in the end, what we are trying to figure out is what is one of the unknowns, given the 6 quantities on both sides of the equation. If 5 of them can be determined, then the only one left is going to be your unknown. And with that one unknown, one equation, you should solve for the equation. So for the first 2 learning objectives there, we are trying to look at the energy aspect of chemical and physical processes there, and how do we calculate the enthalpy change for a chemical reaction. So the third learning objective there, we want to introduce what we call the Hess law to calculate the enthalpy change for a chemical reaction. What is Hess law? Well, Hess law has many different expressions there. Okay? So one of them would be the change in enthalpy for a reaction equals to the enthalpy of formation of the product minus the enthalpy of formation of the reactant. Now this equation we actually showed you when we introduced the term enthalpy here. So the enthalpy of a enthalpy change for a process equals to the summation of the enthalpy from the product minus the total enthalpy from the reactant here. Okay, so when we introduce the state function, we say, well, state function is something that doesn't matter how you go from point A to point B. It's always the total amount in the end minus the total amount at the beginning. Okay, so that is one type of statement, one statement regarding the Hess law. The enthalpy change for process equals to the enthalpy of formation for all of the product minus the enthalpy change, enthalpy of formation for all of the reactants there. So in a sense, if you're having a chemical reaction, when the 2 reactants reacting with one another, you have to break all the old chemical bonds. And then when the product is formed, you are recombining different types of atoms together. When the chemical bond is formed, the enthalpy of formation is actually, from the product, is the amount of energy being released when all the new chemical bonds are being formed. Now that energy minus the energy required to break all the old chemical bonds. Well, that's the net change in the enthalpy there. So Hess law is about the net change before and after. And Hess law is the law that we use to do calculations about pretty much all state functions there. It's a simple addition and subtraction. Okay, you just have to, when you look at the equation there, you just chemical equation there, you just have to identify who are the reactants, who are the products, and then it's always product side minus the reactant side in terms of enthalpy or Gibbs free energy and all that. Now we did not talk about Gibbs free energy or entropy, and that is the topic in thermodynamics. And those of you who are taking Chem 102 later on in Chem 102, there's a chapter dedicated to thermodynamics there. Okay, so this is one expression of Hess law. The other one is that if you have a reaction,